Hello everyone, welcome to the Karpenter SIG Autoscaling, going to call it working group for lack of a better word, synced for Monday the 10th of July 2023. We're going to be treated to a sort of walkthrough from of Karpenter from Jonathan today. So yes, I think that's all we have on the agenda, but yeah. Do you want to take it away?
Yeah, sure. Let me go ahead and share my screen. Well, maybe. Hold on. Of course, it's a perfect time for Zoom to tell me I can't share my screen.
Yeah, many times I've done that. Redid the laptop and then go, oh wait, I need to give it all the screen sharing permissions again.
One thing. I'm gonna have to rejoin. I'll be right back. Let's see if it works now. Amazing. Okay, cool. Okay. Yeah, so I'm basically going to just start giving kind of the high level architectural overview for Karpenter, some of the philosophical, I guess, things which are probably relatively similar to CAS. And then we can kind of briefly look at like a demo of actually deploying some of the configuration for Karpenter and how it reacts to pending pods and things like that. So high level configuration for Karpenter, for those that aren't necessarily familiar with it. Karpenter has kind of two high level configuration pieces. It has the provisioner and the node template. And so the provisioner is effectively a way to define like the world of options that Karpenter can deploy inside of. So for a cluster admin that's setting up Karpenter on the cluster, they would deploy provisioner. And then they would also deploy a node template alongside the provisioner. With the provisioner has a field called a node template ref inside of it, or I guess provider ref right now, which references that node template. But the provisioner is kind of the cloud neutral configuration component, and node template is like the cloud provider specific configuration component. So for AWS, it's the AWS node template. So inside the provisioner, you would define things like requirements, labels, annotations, taints, and then Karpenter effectively takes that configuration, overlays it with the pending pods that are present on the cluster, and determines like a match between those pending pods and any provisioner options that it might have, and then provisions nodes given that node template and provisioner kind of overlay. So the requirement set is very similar to the Kubernetes requirement set, at least in terms of the way that it looks. It is actually a v1.node selector requirement. So it has a key and operator values. You define kind of generic Kubernetes keys. So things like instance type or region or zone, you can define these things inside of the requirements. You can also define Karpenter specific concepts or even cloud provider specific instance labels. So for instance, AWS has things like instance family, instance generation. We have things like the hypervisor that you want to run on. So you can define these things inside your provisioner and basically kind of scope down the total options that a developer who's deploying a pod might have. So the cluster admin can kind of configure that world and set that thing up using the provisioner. And then you scope it down, you define labels, which also kind of interact with the pods and provide that overlay. And you can also define like annotations, some of the things that are a little less like restrictive on the actual pod scheduling, but are more informational. And then obviously taints that are responsible for determining the match and the scheduling requirements as well. So that overlay combined with the node template, which is not driven by, like the node template is not necessarily going to affect scheduling, specifically because all the scheduling simulation logic that Karpenter does is specific to Karpenter core and specific to the cloud neutral component. Node template is more responsible for just determining like the specific settings that are needed once the cloud provider gets a handle on what it actually needs to launch, and then determines like all the settings that need to be provided to the APIs that will then be launched by the cloud provider. So I guess one thing to note about how that handoff is done is Karpenter has this concept called a cloud provider interface. It is literally like an in-memory interface in a Go struct. So if you were to implement like the Karpenter core interface and you want to interact with like Karpenter core packages, you would have to define this cloud provider interface. And that interface effectively defines like what it takes to create a instance, what it takes to delete an instance, or create a machine, delete a machine, get it. You use that interface to get the types of instances or machines that you can launch. So that's all defined in the cloud provider interface. So there's effectively a handoff mechanism. So Karpenter will take all this configuration, take all the pending pods in the cluster, determine the ones that match best, and then provide all the possible instance types that it can use and to launch the capacity, and then hand that off to the cloud provider for the cloud provider to figure out like how it should actually launch that capacity, and then hand that back to the neutral component that will then do additional lifecycle handling effectively. Also, if anyone has any questions as I'm talking, feel free to chime in or jump in at any point. I don't mind being interrupted. So high level architecture kind of has three main overview kind of high level things that Karpenter does. There's the provisioning component, which is the thing I kind of just touched on, which is it's watching pending pods, determining which provisioners can match those pending pods, and using that as templates for how it can actually launch the node. And so once it determines the types of instances that it can launch with the pods and the provisioners that's been given, it uses that to launch the cheapest, highest available capacity for those pending pods, and then hands that off to the cloud provider. There's the lifecycle component. So at the end of, I'll get into this in a second, but at the end of the provisioning loop, there's effectively a handoff that's done that says, here's all my requirements and the options that I have, and the taints and the labels and the annotations that I've been given, that I've done a scheduling simulation to say like this is what I need to launch. And so I create a thing called a machine custom resource, which is kind of the third custom resource component that is not configuration that Karpenter has. So there's the configuration side, which is provisioner and node template, and the machine is more of like an internal implementation detail, which is at the end of my scheduling loop, I create a machine that captures basically the requirements that I need to fulfill in order to launch this capacity, and all the labels, taints, all the other information that are specified there. So once that machine is launched, then the lifecycle takes over and is responsible for basically reconciling that machine to launch that machine, launch the capacity, and then maintain its health. I see Marcin has his hand up.
Yeah. So what is the exact difference between this machine and node template? You said that node template has basically everything on AWS side, and machine template is kind of a node template, but in a specific context.
Yeah, effectively. That's probably a good way of explaining it. Like a node template is the templatized version of those specific. So a machine will have a node template ref inside of it that will say like, this is the node template I need to launch with. So that won't change. That dynamic piece that is like machine specific context that you're talking about is mainly driven by that provisioner pod overlay. So the provisioner specifies like a high level set of requirements that the pods can schedule inside of, or the capacity can schedule inside of. And then that's further constrained by the pods that are pending at that given time. So there's a scheduling simulation that's done that says, okay, here's like the maximal set of requirements that I can schedule inside of, and then, or the instance types that I can use given my provisioners. And then that gets constrained by additional pod constraints. And that constrained set of requirements is then passed into the machine to basically say like, okay, here's like contextually that overlay between that provisioner and that pod, or those pods that I plan to schedule to this.
So
this node
machine represents a request for a node, basically.
Yes.
Okay.
And that's only driven by the fact that we, unfortunately, like nodes are, I guess they're registered by the kubelet, and they're updated by the kubelet in terms of like status information, and you can add status information, but you can't. We were struggling to drive like launch-based reconciliation through node. It doesn't really work well.
We
Kubelet
used
has-
to,
Yeah, go ahead.
just for some history, is we used to not have this machine object, and we created the node object ourselves. And so we stored all of that state on the node object, which worked well, except for a couple of edge cases, and we kept on running into systems that assumed things about the node, which we eventually had to move to this other model where we store. I think the way you put it, like calling in a node request, is we actually considered that name as we were naming the CRD. It's you can kind of think of it as like a parallel to the node. It's the object that manages the node, but it's where Karpenter stores all of its specific state.
Mhm.
Since Messiek is, you want to go Messiek? I may be butchering that, sorry.
Sure. So I'm trying to understand the machine better. So is this, because you mentioned it's like a request for a node. So is it more of a request, or is it just a representation of the VM or instance that maybe is or maybe isn't a node quite yet because of like life cycle issues? I'm trying to figure out, does the machine exist before the actual VM is created, or separately from it, or is this, does that question make sense? I'm not sure how. I'm trying to
I think
understand the life cycle here, basically.
yeah. I mean, I was kind of trying to drive like the overview of these three components and then talk about each one individually. This is kind of the architectural diagram effectively for the provisioning loop, but it does exist prior to, so it's the request object for a actual instance being launched inside of the cloud provider, whichever cloud provider that is. And then eventually it expects the node to be registered that kind of matches up with it. But it is also like the lifecycle maintenance component that Karpenter uses. So like Ellis mentioned, like we drive all of Karpenter's decision-making logic through the machine because it handles the creation flow and the termination flow. So the spec for the machine, this will help more tangibly. The spec for the machine like defines a set of requirements, which are like the provisioner requirements, but constrained down based on the pods that we think will schedule to that node once it's launched. And so we say like, here's the constrained set, launch an instance for me. And then eventually the node will register, and then we will store status information back onto the machine that will help us like maintain and basically manage the life cycle of that node. But it's kind of like the Karpenter driven place to handle creation, termination, scheduling, simulation. But it does exist prior to the node joining.
But sorry, if I may ask one more quick question, or?
Yep.
Because I can see it also has multiple values for instance types. So is it basically, it just says it's one of those instance types, or is it, and then, so the machine is created first and then the instance type is selected. Is that correct? Or?
Correct. So the machine is created first. There's a set of possible instance types that it could launch with. Maybe AWS is maybe a good example here because that's the most tangible example we have. So we launch with, we basically provide the set of instance types to AWS specific APIs, and then AWS hands us back information on which instance type is the best, that like it has some internal information on which instance type is going to be the cheapest and the most available that are not available publicly. And so you hand it all these instance types, it gives that information back, or it basically says like, here's the best instance type that we think we can launch at this time, given availability and price constraints. And then we take that and say, okay, we launched with this instance type, and we store that information back into the status information on the machine.
All right, great. Thank you. That's super helpful for understanding it. Thanks.
We happen to do that server side in our cloud provider, but you could do it client side as well. A basic use case for this is working with spot markets, which are typically quite constrained. And so that flexibility allows you to kind of, for example, if you have 20 different instance types and potentially 3 different zones, you have 60 different offerings to traverse. And so you could client side try each of those offerings by price until you get one essentially that is available. AWS has an API called the Fleet API, which does all that math server side. But the flexibility is one of the core tenets of Karpenter, or kind of one of the core design principles that we built around, was being able to kind of have the opportunity to, it's largely driven by how diverse EC2 is and how hard of a problem it is to do bin packing on the cloud provider side. But that flexibility essentially enables the cloud provider to give the customers lower prices and better availability of their instances.
Is there one of the problems that we've run into at Acquia, and Suraj is also on my team at Acquia. One of the problems that we've run into is that the cluster autoscaler makes a lot of short-term decisions and doesn't make medium to long-term decisions. So in other words, if when trying to identify what would be the cheapest thing right now that would satisfy the current unschedulable pods, it will very often push us into C5s, and then we'll very quickly end up memory constrained on those. Is there any sort of way that we've taken some other measures to make sure that things end up on the long-term optimal memory to CPU ratio, no instance types? But is there anything that Karpenter does that will revisit and say, hey, I've given out a lot of C5s that should have been M's or R's, and shuffle those things around?
Yeah, so Karpenter right now has a consolidation mechanism, so I guess I'll take a step back. There's two main things. So if you're talking about on-demand based instance types, that's one thing. Obviously, for spot-based instance types on EC2, like that's where Ellis was talking about, like there's a server-side decision that's made in terms of like availability, obviously. So there's like a long-term decision made for spot instance type launches when it comes to things that we think won't get capacity constrained and will be like reclaimed. So that's one. If you're talking about even on spot or talking about on demand, making long-term decisions, yeah. So there's an immediate decision that's made by Karpenter to actually launch the capacity so that your pods are scheduled as quickly as they possibly can be. But then there's a further decision that's made down the line, which is the consolidation mechanism, which is responsible for basically doing scheduling simulations across nodes, with like considering the highest, like the nodes that are the most underutilized, the nodes that don't have the best CPU to memory ratio and are like, maybe you can imagine that a node is 50% utilized by the pods on it. And it will try and do a scheduling simulation to determine, can these pods potentially schedule to other nodes that I currently have in my cluster that would make my utilization for my cluster better? Or can these pods also like reschedule to a new instance that I could launch that would be cheaper or would be better for these pods? So nice. We do that reevaluation. You can enable that through the provisioner. That basically, I think that provides the mechanism you're looking for, I'd imagine.
Yeah, in our experience, the cluster autoscaler doesn't end up shifting things back to the M's and R's down the road. So we've had to take some other measures that introduce a little bit of introduce additional constraints, which we have to be very careful about to make sure things go to the right place in the first place.
How do you convey that?
Think there's an interesting discussion to have around the differences between Karpenter and cluster autoscaler, but just given the time, can we focus on the Karpenter architectural overview today?
Cool. Okay, we kind of touched on provisioning, but I'll quickly run through this. So similar to cluster autoscaler, Karpenter will observe pending pods that are present in the cluster. It observes the cluster state in general. So kind of observes the total cluster state to determine, okay, can these pods schedule to existing nodes? So it does the scheduling simulation in memory, similar to the kube scheduler. It'll determine, can these pods schedule to existing nodes? If they can, it won't take any action. If it thinks that pods can't schedule to existing nodes, that's when it will launch capacity. And that's when we get into the discussion on a machine request or a node request or machine, or basically a response that says, okay, here's the pods that I wanted to schedule, and they have certain affinity, label requirements, whatever. They have certain constraints, and we need to match those with the provisioner that can actually be used to provision a node. So Karpenter will watch these pods, determine that pending pods need to schedule because they won't schedule onto existing nodes. It'll find provisioner matches, and then it will create a machine which will be that provisioner requirement set constrained to the set of requirements that the pods need. and generate that machine object. Oh, and I guess I forgot to mention, so it will go to the cloud provider to get any instance types that it needs to, or get the instance types that it can launch with. So it'll grab all the instance types from the cloud provider specific APIs, and then use all that information combined with the provisioner, combined with the pending pods to launch a machine, which is this component here effectively, which will, I guess the spec is probably the most interesting part. So it stores the requirement set, like I mentioned. So this gets constrained by the provisioner requirements and the pending pods. It stores the total resource requests that it thinks will launch onto the node. So when it's doing that scheduling simulation, it will actually simulate pods scheduling to that machine or that node request, and it'll sum up all those pod requests and store that information inside of the spec. It will reference out to that node template that we talked about earlier. This will probably get renamed, but currently it's called machine template ref. It references a node template, slightly confusing. We're talking about the API rewrite next week, but it'll reference out to that node template, which will give it the information on the settings that it needs to use to actually talk to the cloud provider specific APIs when it launches. And it'll also pass in all those labels and annotations and information from the provisioner. I guess the other thing that's not specified here is it specifies taints. So basically everything that's in the provisioner gets put into the machine, is constrained down, and is used as like a node request to launch the capacity. So I'll try and break this down, and it's numbered. Basically a reconciliation loop for launching a machine. So once the machine gets created, there's a watch that happens inside of Karpenter with Karpenter controllers. It'll watch the machine, which is one that then sends once it sees that new machine has been created, it'll send a request to create that machine to the cloud provider specific APIs. So it calls out to the interface, at which point it's up to the cloud provider to define how it's going to actually create the capacity. And so for AWS and EC2, it'll call out to create fleet, like Ellis had mentioned. And create fleet will give us back the instance type that it thinks, given the set of instance types that we pass to it, it will give us back the instance type that it thinks is the best instance type that could launch right now, given availability and price. And so we get all that information back along with the ID of the instance that launched, and get all that information back into the same machine object that we used to launch. So we kind of do that classic handoff between, here's my spec, I'm going to reconcile it, and then I get the status information back. So it propagates those machine details back, which causes an update to the status and some of the label information that's stored in the machine. So when we're talking about the machine and the node request representation of it, we use the labels and we use the labels and the taints on that machine to also represent the in-flight capacity of that launch. So effectively, once we update the status information and the labels back onto the machine, as soon as we have that information, we can start doing scheduling simulations in another round. So we basically create a set of machines in the provisioning loop, and then we have to sit there and wait for a little bit because we don't know what the resolved capacity is going to look like yet. So even if new pending pods come on, we can't schedule them yet because we don't know how those requirements are going to interplay with the nodes that are actually going to get launched. Given like affinity requirements or topology spreads or any of these things. And so we have to wait for the cloud provider capacity to actually resolve that information. And once we resolve that information, we put it back into the labels, and now we can start doing some scheduling simulations again. You can imagine, like Ellis mentioned, like historically with the node, it was a very similar idea. Like we'll launch capacity. We'll actually, instead of creating a machine object, we would historically create a node object that would store the labels information. And then we could start doing scheduling simulations as soon as we created that node. But the idea there is obviously there's going to be some latency between the time that we actually launch the instance and the time that the node actually registers to the cluster. And we don't want to sit there waiting for that node to actually register. We want to react as quickly as we can. So we resolve that information back into the machine, and we use that for scheduling simulation as soon as the instance gives us, or as soon as the cloud provider gives us that information back. So that resolves back.
Workflow, Jonathan, can you explain a little bit on how long it takes for that resolution to happen?
Yeah, I don't know if we have like specific benchmarking metrics on it, but I'd say on average it takes seconds, right? It's like a few seconds for it to actually like launch and then come back. You're talking about the life cycles piece, right? I think so. The provisioning piece is like obviously dependent
Yeah,
on,
just like for any the benchmark here, or maybe the comparison point would be how long how long it takes for the auto scaling group to react. Like as far as I understand, like the analog here is changing the replica count on an ASG or on the node group in CAS. As far as I understand, the second that waiting period doesn't exist in CAS, right? Because you can assume that the instance is identical to anything else in the group. Whereas for us, because of the flexibility, we have to wait a couple of seconds to get that information back, essentially.
so we could call out. Yeah, so we'll get that information back, start doing scheduling simulations if there are additional pending pods that come onto the cluster. And then meanwhile, the node or the instance is launching and all the startup scripts are running, and the node will eventually register onto the cluster. And once it does, Karpenter will see that node registers. It will match up the machine and the node right now through the provider ID. So the ID is the information we get back from, at least from EC2 and AWS, and the cloud provider will give us that provider ID back based on the constructed cloud provider ID, however it's specified within that specific cloud provider. So we'll put that back into the machine once we get that or the resolution from that create call. And then once the node registers, it should have the same provider ID. And so we'll match up those machines and that machine and that node. And then effectively, once the node registers, it is the scheduling representation for like the de facto scheduling representation for any simulations that we might do. So Karpenter will use the machine as like the management object. So when we're doing things like consolidation, like we were talking about earlier, and I'll get into it in a sec, but once we're doing like deprovisioning logic, it will do that logic, like it'll drive that termination flow by deleting a machine, which will kick off like a termination, the whole cascading termination that will eventually like cordon drain, delete the node. But the node is like, because the kube scheduler is using the node is like the de facto scheduling representation. So once that node registers, then we use that. So when we resolve information back into the machine after the launch, there's like a set of information that we resolve, the labels, annotations, things like that. But then there's also the allocatable information. So we'll do an estimation on what we think the allocatable will be, which is generally like extremely close to the actual allocatable of the node. But say some user does something wacky in their startup script on the kubelet arguments or something like that, it might be off in some way. Generally, that's not good behavior, but anyways, we resolve like simulated information, allocatable details to determine how, like what the capacity of that node is into the machine. And then once the node actually registers, then that becomes like, okay, here's the actual capacity and allocatable for the node. Here are the labels for the node. And we use that for all of our simulation logic on any new pods that might come in.
Really quick, is the machine associated with the node or the ASG?
It's absent of an ASG. So the machine lives on its own. So the machine is like just an EC2 instance, effectively, at least in AWS. It's an EC2 instance representation. And it's also correlated with the node. So we use it to represent that node object before the node actually comes on the cluster.
Okay, so if we needed to scale up a number of things from one ASG, we'd create a number of machine CRs.
Yes, I guess if you were representing an ASG with machines, yeah, you would basically do it that way. You'd increase the replica count of that. Like if you can imagine there's like a machine set, or even on a provisioner today, it's all dynamically scalable replicas. Effectively, it's like an auto replica based on like, you can imagine like you could have an infinite number of replicas that are specified in your provisioner that you can fulfill based on new pending pods. But you can imagine there's like a static replica field that you said like 6 or 7. I want 7 replicas of this provisioner. And so that's like a machine set in a way. Like that provisioner is going to generate machines, a set of machine replicas that are going to then launch instances and are going to resolve into nodes. So you can imagine you could create a machine set that would create machines that then, does kind of what you're saying with ASG.
Gotcha.
One thing to note on, so I did talk about the status information. There's a whole set of status information that's resolved back, including that allocatable that I was talking about, which we use for scheduling simulations. And then there's also a set of conditions that are specified and Karpenter uses to maintain management of the object and to understand like what state the object is in. There's a launch status condition that tells us whether the machine is launched successfully. There's a registered status condition, which tells us whether the node has registered for that given machine. There's an initialized status condition, which we use specifically for deprovisioning. So one thing to note here is that this number 8, which is that Karpenter will mark the machine as initialized. Initialization is effectively a concept that Karpenter uses to determine if it can start deprovisioning nodes. So Karpenter has various deprovisioning mechanisms. One of them is consolidation, which is the underutilization mechanism, which is the way that Karpenter says, okay, this node is underutilized. I need to reschedule, or I need to delete it because these pods could schedule to other nodes in the cluster, or I need to replace it because there's a cheaper version of this instance type. But there's other deprovisioning mechanisms. There's expiration, which we effectively have customers that are saying like, I want to roll my nodes because I want a security update within a certain time span. So I have a expiration timeout on my nodes, 30 days or something like that, and it will see when nodes are expired and then roll them. Emptiness, which was like kind of the precursor to consolidation, which says as soon as there are no pods that are scheduling on my node anymore, I just want you to deprovision it after a certain amount of time. So there's this field called TTL seconds after empty, which says, okay, here's how long I want you to keep my node after it's empty. If it's, past this point after it's empty, then deprovision it. And then there's also a mechanism that we're actively building out right now called drift, which says, is my node that's currently launched drifted from my configuration that I've specified? So if I change things in my provisioner, if I change things in my node template, do they match my current set of nodes? If they don't, I want you to roll them, which is also somewhat of a security concern. So because you can specify things like image inside of your node template. And let's say you update your image because you have a security patch, you want to roll your nodes for that. But initialization is most, I guess it was most important in terms of consolidation and emptiness, primarily because initialization basically tells us like, when is this node in a state that we can actually like assume that pods have scheduled to it and we can operate on it effectively. So I guess a good example for that is extended resource support. So let's imagine there's a set of pods that are requesting NVIDIA GPUs, and NVIDIA GPUs require a device plugin that needs to run on a daemon set, and that needs to register resources to the node. So we launch a node, or we launch a machine, which launches a node, and then the node comes up, and then it doesn't have the NVIDIA GPU resource registered, so no pod scheduled to it, and we see the node is ready. And so as soon as the node is ready, we're like, oh shoot, it's empty, so let's deprovision it. So we can't operate that way because obviously the daemon set needs to schedule to the daemon set pod needs to schedule to the node and then register the resource, which is going to take some time. So to get around that, we have this concept called initialization, which is, I guess, four-pronged at this point. It says, are the resources that I requested, so back to like the machine resource requests, are the resources that I requested because I thought pods that I have pod requests that need to schedule to this node effectively. So are the resources that I requested actually available on this node? If they're not available yet, then I won't consider this node to be initialized and I won't operate on it. So in the case that I have an NVIDIA GPU, or I want NVIDIA GPU to be registered on my node, I need to make sure that NVIDIA GPU is actually registered as a resource on my node before I actually act on emptiness or anything like that. Other things are actually like the readiness of the node. Are all the expected taints that I expect to be removed. So one example is the external cloud provider taint. Obviously, external cloud provider taint would prevent pods from scheduling to the node, and that external cloud provider taint can still be there longer than the node goes. I guess the node can go ready, and then the external cloud provider taint could still be there. And so we need to expect that thing to be removed before we say, okay, we can act on it for emptiness or consolidation or anything like that. So that's that like final concept. And that's kind of the effective end of like that launch lifecycle. There's a separate lifecycle that's dealing with those deprovisioning conditions. So we call them disruption conditions. effectively any of those conditions that I listed that are the ways that Karpenter can deprovision nodes are used for disruption conditions. So for instance, like expiration, if we determine that a node is past its expiry, or a machine is past its expiry, then we'll mark that machine as expired in its status conditions, and then the deprovisioning logic is able to see that and then clean it up. Same thing with empty, same thing with drifted. We'll basically add status conditions into that machine that say, okay, this thing is drifted now. So then the deprovisioning controller can then pick it up and respond to it. And so that kind of brings it to the last point, which is how does deprovisioning happen? The Karpenter controller effectively watches for disruption, those disruption conditions on the machine. Once it sees there's a disruption condition that it can act on. So it does, those disruption conditions are added asynchronously to the machine. So they happen, you know, asynchronously in time. And then this deprovisioning controller is responsible for determining what's a safe way to deprovision these nodes, given policy mechanisms. And right now, we currently in Karpenter, we only support, unless the machine is explicitly empty and there are no pod scheduling across the board, we support rolling. I guess, well, I'll take a step back. So for certain conditions, we basically support like synchronous one at a time rolling of nodes and replacement. For consolidation specifically, we will like deprovision an M-to-1 set. Effectively, we'll say like, here's like a set of nodes that we can deprovision down, and we'll deprovision them down and replace them with like a single instance. But we necessarily will basically restrict the amount of parallelism that can occur due to, you know, different concerns about the ability to like we don't want to like boom expire a bunch of instances like immediately and then provision new instances, and then all of a sudden all the pods are, you know, gone. We do respect PDBs. So if PDBs are specified on a set of pods that are scheduled on a node, and those PDBs would block the node from being deprovisioned, then we won't deprovision that node. And then we're currently, like Nick is actually working on policy mechanisms for users to specify higher parallelism. So right now, certain mechanisms only support like one replacement at a time, but you can imagine that might slow some things down, especially on large clusters. So Nick is working on building out basically the ability to support higher parallelism for some of these things in a safe manner. But let's imagine there's either a set of empty nodes that we're deprovisioning all at once, or there's a single replacement node that we need to, you know, spin up a new node for and then spin down the old node for. Effectively, we watch for these disruption conditions, and then we'll spin up replacements if we need them, or we'll deprovision empty nodes if they're no longer needed. So if, you know, a bunch of machines are disrupted and there's no pod scheduled to any of them, they'll just get killed as soon as all the disruption conditions are observed by the deprovisioning controller. If there are pods that are scheduled to those machines, then we need to launch a new replacement for it. We'll see, okay, we've disrupted, like this machine has been disrupted. We need to spin up a replacement. And so that'll kind of trigger the lifecycle flow. So that will spin up a new machine, which will trigger the whole lifecycle flow, which will launch a new node. And then we'll eventually get that node that gets created on the cluster. We'll ensure that node is like successfully initialized, that everything has been registered like it should have been. Everything is good and going well. And as soon as that node is up and running and fully initialized, then we'll propagate the termination for that old node. So we'll wait for initialization, we'll initiate the termination on that old machine, and then terminate that instance by doing a cordon drain and delete logic on that old machine that we had some disruption condition. Yeah, Marcin.
How do you do upgrades? Is it via the provisioning or some other mechanism?
Upgrades for like a
image upgrade from Kubernetes version A to B.
Yeah, so for the actual worker node upgrades, so if you did, so for instance, in like AWS EKS, if you did a control plane upgrade, you would upgrade your control plane to the newest version. Your worker nodes would be on an N-1 version, and then you would roll your N-1 version nodes. Right now, there's two primary mechanisms. You can either do it through, well, I guess there's three mechanisms. You can do it through like the TTL expired mechanism, which is kind of the historical mechanism for rolling your nodes. So you set some TTL on your nodes, Once they expire, they will go through this deprovisioning flow. So they'll deprovision, we'll launch a replacement because there are pods on that old machine or that old node. And that new node will have whatever image is specified on your provisioner and your node template. So in AWS node template, you can specify a specific image that you want it to launch with, and that image might change over time, obviously. So we have this concept called an AMI selector. So you can select on these AMIs with tags, or even by default, we'll give you the latest EKS optimized AMI. And when you get that latest EKS optimized AMI will change over time as upgrades come out. So when you launch that new node, it's going to use that new image. And so on a control plane upgrade, for instance, if you go from 127 to 128, when we discover that AMI, we always use the server version, the API server version, to discover that image. And so we'll see that we need to use a 128 image now. And so we use that 128 image and we launch that new node. And so now that new worker node comes up with that new image.
So basically, the upgrade process is built into Karpenter, and you change the configuration as soon as you realize that there is a new version.
Yes. So once the node is when we go through that create launch process and that node is getting launched, it will discover an image. And when it discovers that image, it always uses the server version, the API server version, to discover the control plane version or the worker node version it needs to launch with. And so the upgrade is basically driven by the deprovision, or it's driven by the discovery of that new configuration on new nodes. So if you deprovision the old nodes and you get new nodes, those new nodes will have the newer configuration.
Okay, that I understand. The question is, what about the existing nodes?
So the existing. Oh, you got it, Nick?
Yeah. So this is actually one of the core deprovisioning mechanisms that we call drift. And basically it works the exact same way as like a deployment drift. When you change a deployment, it'll roll all the pods that are owned by the deployment. So like if you change the node template to resolve to a different value of the AMI, then that will detect that as part of deprovisioning, and then it'll go through this loop and replace a new node with that. Expiration is a way to eventually do that over some time, but drift is the one that triggers it whenever the resource changes.
And just for a little more color, one of the key ways that this is different than upgrading a node group directly is that the scheduling decision happens again. And so the node launch decision is totally dynamic. There are cases where you have a node that's drifted, and when it's drifted, all the pods can migrate to existing capacity, and you don't actually even need a new node. And similarly, you may have a node that's drifted, and the node that's launched is smaller than the previous node, or potentially even is owned by a different provisioner. And so the dynamism of the launch decision is kind of included in these consolidation decisions, or sorry, these deprovisioning decisions as well. So kind of similarly, from the algorithm's perspective, there isn't really a difference between deprovisioning due to underutilization or drift or expiration or interruption or any other reason. They're just kind of a way that we identify, hey, this node needs to go away, and then we go through a standardized algorithm to replace the capacity, whatever that means.
Okay, thank you.
Yep. So that's effectively the three mechanisms, I guess, at a high level that we operate with in Karpenter. So I'll briefly show a demo of what this looks like on a cluster. So here we got, hopefully, maybe I need to zoom in a little bit. Hopefully everyone can see. So right now I got a Kubernetes cluster. It is running Karpenter. Zoom out a little bit. So it's running Karpenter. It has, I think, a couple nodes on it right now that are running in ASG, that are actually running the Karpenter deployment right now. And if we're thinking about like a generic deployment of provisioner and a node template, let me just jump over here. all the pods to schedule across separate nodes. And it also has topology spread constraints so that it will effectively ask it to spread across different zonal topologies, spread across zones. So Karpenter actually has zonal discovery logic. So as part of that instance type discovery, Karpenter will discover all the zones that exist within for all the different instance types, and then it'll use that zonal discovery to effectively do that topology spread across all the zones it knows about, rather than just about the zones that match the pod, like similar to how the keep scheduler would only have like a very constrained idea about the zones that it could schedule to. So it does zonal discovery logic, and it'll spread across, across all those different zones. So for these 20 pods, we'd effectively expect them to schedule across 20 different nodes, and then be spread across all the zones that exist in this region. For the provisioner, very minimal configuration that you need for the provisioner, at least at the start, and you can use, basically Karpenter will default a bunch of things for you if you don't specify anything. So all you need in the provisioner is literally a provider ref that references the node template. And so here I'm just saying, okay, reference the node template with the name default. And so my node template is over here. It has the name default. From AWS specific node template side, actually, you don't even need the AMI family here. It'll get defaulted for you, but AMI family is a concept where you can specify, a set of AMIs that you want Karpenter to provision nodes with. And so AL2 is one of the AMI families. So the AL2 AMI family will provision a node with the AL2 image or the EKS optimized AMI image for AL2. And then you also specify the subnets that it needs to, or one of the subnets that it could possibly launch within, given a subnet selector, which selects subnets based on tags on those subnets inside of AWS, and then a security group selector, which likewise, any of these selector mechanisms specify based on tags on those resources. So for security groups and subnets, you tag your resources, you tag your subnets, you tag your security groups with a given tag, and then you can tell Karpenter, okay, discover these subnets or discover these security groups given those tags. Marcin, you raise your hand.
Sorry, do you need to write this thing by hand, or is it somehow auto-generated for you? This AWS node template.
We have, right now you need to write it by hand effectively. Very minimal configuration, but you do need to, we give a default node template and a default provisioner that you can use within the documentation, but there's no auto generation logic that Karpenter does specifically because the user does need to provide some sort of guidance to Karpenter on what it should be using when it's launching nodes.
Maybe a silly question, but subnet selector and security group selector sounds like an advanced feature, right? A little bit.
I think
this is one of the differences between EKS and GKE. As far as I understand, a GKE cluster is aware of its subnets and its firewall rules, whereas EKS clusters aren't aware of them. So if you were on GKE, you wouldn't need, and the whole point of the node template is essentially it's provider specific. So if I were writing a provider for GKE, I don't know of any config that I would need here at all. It's possible you could have a fully defaulted node template for GKE because GKE is able to self-discover its subnets and its firewall rules.
Okay, cool, thank you.
Yep. Okay, so if I deploy this node template and this provisioner to the cluster, nothing should happen at this point. So we should still have the same number of nodes. Karpenter shouldn't do any reaction to anything because there's no pods to actually schedule. But as soon as we schedule, or as soon as we deploy the deployment, it's going to obviously bring up a bunch of pending pods, and Karpenter is going to react to that using the provisioner and the node template that we just defined. So if I deploy the full deployment to the cluster, one thing that we should see, and speaking about the machine objects we were talking about earlier, machines should start to launch. And so these machines are launching, and I'll get off the watch so we can see a little bit better, but they effectively launch and give us some high level information in the JSON printer columns. But if we look at one specifically, it's going to have all the information we were talking about earlier. So it has label information, which at least on this provisioner, like you would specify labels either by constraining your requirement sets or by specifying like static labels within the spec. So you can specify like a static label set here. But we didn't do that. So all these labels that are propagated are coming from the cloud provider resolution and from our kind of our Karpenter's inherent knowledge of the requirement sets that it launched with. So we get all the information about the instance and all the Karpenter specific labels, as well as the Kubernetes generic labels that are put back into this machine for scheduling simulation. So obviously like architecture, OS, capacity type, which is a Karpenter concept, but on demand is the capacity type we're using here. You also get the regional information, the zonal information, the instance type information, that all gets resolved. These machines are owned by their provisioner necessarily. So if the provisioner gets deleted, the provisioner is again representing the world of these nodes or these instances and these machines. So similar to an ASG, if the ASG goes away, all the underlying nodes go away, provisioner goes away, everything that was owned by the provisioner gets deprovisioned unless you orphan it specifically. And then the requirement set, which is constrained, and I guess I did miss, if we look at the provisioner that actually got created here, it is defaulted. So there are some sensible defaults that Karpenter uses. It by default uses Linux. It by default uses AMD 64. It uses on-demand capacity type by default, at least on AWS. And then it specifies kind of a generic set of instance categories and instance generations that we think that users should be using if they're trying to launch instance types, unless they specify otherwise. Yeah, Marcin.
So one question about this owner reference. You said that if you delete a provisioner, you can delete all of the nodes that are belonging to it. So by a small typo, you can blow up half of your cluster, right? Or is it some mechanism that prevents it?
So you're asking if I delete, like, accidentally delete
provisioner A instead of B, I can remove half of my cluster by accident, or is it some confirmation or whatever?
Yeah, it's a good point. I think it's similar to like we would expect that our users would lock down their policy well enough that they wouldn't just allow somebody to outright delete a provisioner without some sort of additional, policy checks that are involved in being able to do that. So I think in general, you wouldn't allow somebody just outright access to all your provisioners that would be able to do that. I mean, it's similar to ASG APIs. Like if you were to outright delete your ASG API or your ASG, you would obviously expect that everything under that would go away. I don't know, Ellis, if you have any thoughts on.
Yes, but usually if you, for example, delete some, I don't know, notebooks or whatever in the UI, you get like a confirmation. Are you sure that you want to delete it? Or if you use command line tool, you usually need to, I don't know, type yes or whatever. Here it goes a little bit without notifying user about the potential impacts.
Yep.
Yeah, I mean, because we're using, I mean, you could imagine, I'm sure you know what happens when you type kubectl delete node in Kubernetes, like, --all is extremely disastrous. The VMs end up continuing to run, but Kubernetes isn't aware of them. There's all sorts of really disastrous things you can do. You can delete kube system, for example, or various things. You can kind of think about this as the lower level interface. Most customers who are interacting with these CRDs are interacting with them via Terraform, many of them via UIs. You could imagine building a flow built around Karpenter that the customer potentially isn't even aware of the provisioner. Many of our customers do this actually, as they kind of wrap Karpenter with their own operations team's opinions. I definitely agree with you that these deletion actions broadly in Kubernetes can be really disastrous. One of the things that we point our customers to is policy agents to protect against this. So just to provide additional levels of controls to determine what can easily be deleted or not.
Okay, thank you for the explanation.
kind of, I guess, wrapping up a little bit. So this machine has basically like a lot of this requirements logic or requirement specific information that's specified in the provisioner, but it also has the instance types that we simulated we can launch these pods on. And here, so we specify our full set of instance types that we can launch with, and those are passed to the cloud provider, along with the zone that we think we should launch in. This zonal one is there primarily because of the topology spread. So we did a topology spread simulation and we said, okay, we need to launch in this zone because of to fulfill our topology spread constraint for this machine. So we specify that requirement here. And then again, the resource requests that are specified here, all the resolve status information, including our simulated allocatable and simulated capacity. And then status conditions that give us information on the state of that node or the machine as it's launching. I think Maciek was first.
Thanks. So I have a question. I noticed there is a provisional label, and you can have more presumably since there is a default one. So I assume you select your provisional with node selector, right? If there is a label, is that correct? Okay, and then what happens if I specify node affinity with operator in and like multiple values? Can I do that? Can I basically specify multiple provisioners on one pod? And if so, what would be the result?
Yeah, I believe you can. So you can specify node affinity with multiple values, and you would, so Karpenter is a concept called weighting, like WEIGHT. So weighting is basically on the provisioner would tell Karpenter to order your provisioners in a certain way. So when we're doing like that scheduling simulation, you would have, I try provisioner A before I try provisioner B because the weight on provisioner A is higher. So without that weighting, if you specified a node affinity with multiple values, you would effectively get a random choosing from Karpenter of the provisioner that's going to launch a node with. If you have weighting that tells Karpenter which ordering it should go with, it'll specify the one with or it'll give the one with the highest weight.
So if you have weighting, I'm trying to figure out, can I basically kind of do a preference with this where I say I prefer this particular like provisioner config, but if for some reason I cannot go get those instances, like this is my fallback strategy, can I do that with multiple provisioners and weights?
Yes, that's effective. That's the way that we tell people to do fallback today. So.
Hey, thanks.
It's quite similar to the priority expander, except that it's almost kind of like there's multiple built-in expanders that you can overlay on top of each other, essentially.
Okay,
It's like a cost expander and a priority expander.
Suraj, I think you were next.
I had a question around the simulation. I had a chance to go over documentation of Karpenter, and my understanding is that we don't import scheduler code. And please correct me if I'm wrong. And if my understanding is right, I guess my question is, do we have to reproduce the logic of scheduler in Karpenter? And if yes, how do you manage the drift with the upstream?
Yeah, so this is like an active question. So right now we're just maintaining, like basically keeping up with the changelog and maintaining, like keeping an eye on when things are updating in newer versions of Karpenter or newer versions of Kubernetes as scheduling changes. So for instance, I think in 1.2.7, there's some changes on how topology spread handles like certain pods based on whether they, there's some differences in topology spread, I believe, in 1.2.7. Which we haven't added in Karpenter yet. And so we're right now we're having to kind of go through this manual process of keeping track of what changes are coming and then porting them in. Thankfully, the scheduler doesn't seem to change like too much between different minor versions of Kubernetes. Like it seems to be fairly, obviously it seems to be fairly stable at this point. But when changes like this happen, like right now we're keeping a manual eye on them. I think the goal would be that we'd be able to eventually do upstream like scheduler conformance so that we're aware, or some sort of, whether it's upstream conformance that we can port into Karpenter or some of our own conformance testing that we can ensure that, new scheduling code as it comes out, we validate it against Karpenter's scheduling and make sure that everything works as we'd expect. Fortunately, we're not at that state right now. So we're yeah, we're effectively just keeping an eye on things as they come out and porting them in and opening issues and making sure that we keep up with it.
I see. Thank you. That answers my question. Sorry, I have one more question. I know we are already over time. Is it okay if I ask, or should I ask it on Slack?
I think, yeah, go ahead.
Okay, thank you. My question is more around the machine resource. So if I want to implement a cloud provider, does that mean, given that my cloud provider might need additional settings, would I need to update the fields on the machine custom resource?
No, so we've designed the machine to be genericized. So everything that exists as a spec field on the machine is like generic scheduling requirements details. So the requirement set and then taints and things that should be common across all cloud providers. The stuff that's going to be giving you like cloud provider specific details is this template ref. So this machine references out to this node template, and that node template has all the information that the cloud provider needs specific to that cloud provider. So things like for Karpenter, it's things like the subnet security groups, images, all those details are specified over in node template.
So basically, I would have to implement a custom resource similar to AWS node template, but machine would be as.
You'd have to implement a custom resource, and then you'd have to adhere your. So similar to that, you take a look at the AWS Karpenter implementation, but AWS Karpenter implementation implements this cloud provider interface that I was specifying earlier. So let's see if I can jump over real quick.
Just to clarify, this resource is optional. So as I was discussing with Marcin earlier, if this was on GKE, it's possible that you wouldn't need any configuration at all, and you would just have no provider ref, and everything would just be defaulted the way that however the code happened to work. It's essentially an optional extensibility mechanism to provide vendor-specific fields through a CRD, and it's a way to associate that data with the vendor neutral CRD.
I see. Yep. I think that answers my question. Thank you. Thank you, both of you.
I think we're fairly over time at this point. I was going to maybe touch on how we do. I mean, I think we kind of touched on how we do deprovisioning, but effectively, if you were to enable TTL seconds after empty, or you enable consolidation inside of your provisioner, and then you were to scale down all of your pods on your deployment, Karpenter would see all these nodes are empty, and then it would go and deprovision them all. And that's effectively how Karpenter would go through the deprovisioning process there. And so that, I guess, effectively wraps up kind of the overview and the demo. Hopefully it was helpful. Maciek, did you have a question, or did you just leave your hand raised?
I do have one question, but if we pass time, maybe I can ask it on Slack, and we can follow there. Or if you have a minute, I can ask it now also, because I'm quite curious, but it's pretty into technical details. So
yeah, we can follow up on Slack, and we can have an offline discussion if you want.
Okay,
as well.
Cool. Thank you. And thanks for doing the overview. It was super helpful.
Yes,
Yeah,
thank you.
Thanks very much for taking
Thank
us
you.
over it. I will stick up the recording onto YouTube as soon as possible, so that others can have a watch back as well. Yeah. Other than that, see you next week. We may have a new Zoom link by then. We should be moving out of my work-related personal one, but I'll update the agenda once we do that. Enjoy the rest of your week.